A debugger runs between you and your program. It can be used to control the running of the program and show you values inside the program at various points during execution. That way you can verify that it's running correctly, or you can examine the intermediate values to see why it's not running correctly. When working with higher level languages, providing the source code to the debugger is important because you want to be shown where in the source code you are when you look at the values. But with assembly language, it's not that crucial. What's important is the built-in disassembler. It will show you where you are in your assembly language program, but there is a problem. The mnemonics for all the x86 chip are somewhat ambiguous, and different assemblers require that you write the same code in slightly different ways, so the disassembler may not return your object code to its exact original source, especially where symbols, jump labels, and variables and what have you are involved. A lot depends on how you use your debugger, but probably the most important thing that you can do with one is find out where and why a program is crashing. If your program suddenly blinks out of existence while running, using a debugger can tell you what you did to cause that. But some people like to be able to set breakpoints in a program. This way the program runs until it hits a specific instruction, then it freezes and lets you examine the values and the settings. While you are doing that, you can single-step the instructions and examine the result from the execution of each one. Single-stepping is the same as setting a breakpoint at each instruction, and that's normally the way it's done. A breakpoint can be set by temporarily replacing the instruction with a function call to a special halt routine of the debugger. Then, to move on, the original instruction is replaced before execution continues. Another way to do that is with hardware assistance. The CPU is set so it executes one instruction at a time and halts to turn things over to the debugger. The debugger then checks the address to determine whether a breakpoint has been reached. The second scheme makes another function possible, the watch point. You may be able to set your debugger to monitor one or more data items and catch the point in the program where they change or become a specific value. Whatever process is used by the debugger, it's not visible to the user. All the user knows is that the program stops. The x86 chip uses this second scheme, the hardware assistance. So, with a good debugger, both these features should be available. And it's important that when the program is stopped, however it's stopped, that you are able to inspect all the registers, the variables, and the code. But debuggers are not perfect. You've heard it said that when you observe something, you change it. Nowhere is that more true than with a debugger. I have experienced situations where a program running on its own would crash, but when running under the control of a debugger, it would run perfectly. Also, programs run much more slowly under control of a debugger, so if timing is important, you can get a false reading there too. But for most bugs, they do a fine job. Hundreds of debuggers exist. Most IDEs have a built-in debugger for the languages they support. In this course, up until now, everything presented worked on both Windows and Linux, but that's not true of debuggers. A debugger has to be unique for each system. I will demonstrate how two of them work, one for each system. For the Linux system, the debugger is GDB, the GNU debugger. It's the open source debugger that understands the source code of C and the other languages compiled by the GNU GCC compiler, but it works fine for assembly also. On DOS and Windows, there is a debugger named Debug that works fine with object modules produced by NASM. These two debuggers work in similar ways. They're both controlled from the command line, but they do their jobs a little differently, as I'll demonstrate.